Hello, everybody. I think as it is evident, I am Francesco, not Sabrina, and in this first part of the presentation, we will have a short overview of the historical development and studies about the mechanical properties of materials, mainly metals, but not only metals. Well, okay. Well, please. Okay, so here we go. Sometimes it's just okay. Well, the structural integrity was always an important issue for humanities. Already more than 4,000 years ago, it was written in the Code of Hammurabi that several punishments were written for problems, lapses of houses, including the death of the builder or the death of the son of the builder. It's a very hard time to be son of the builder. Although they know that about materials behavior and the principle of structural integrity, several wonders were built in the ancient world due to the wars, earthquakes, and the passing of time. Only one of them is still with us, the Pyramid of Giza. But anyway, we have still some more recent wonders that we can recall. For example, the Pantheon's dome, that is up to now the world's largest reinforced concrete dome, thanks to a combination of a coffer ceiling that reduces weight and the use of lighter materials like pumice or tufa for the upper rings. Obviously, we can remind the Great Wall of China that exhibits a remarkable structural integrity despite its age and length. Is built with several materials, and it is one of the wonders of our world. And also we can recall the Gothic cathedrals that show some innovation, like the pointed arch, river vaulting, and the flying buttress. These allow to obtain higher walls with a thinner thick. Well, the first studies on the mechanical behavior of materials can be found with Leonardo da Vinci at the beginning of the 16th century, when he described in details an experiment to measure the maximum weight sustainable by nylon wire, considering wires of different lengths. And according to the thoughts of that age, he found that decreasing the length of the wires, the resistance improved. But it was clearly a problem due to the limited capability for the production of these wires. With the longer wires, the probability to have a defect was higher. Anyway, one century, the century after Leonardo da Vinci, we found the first scientific book dedicated to the standard materials, with the discorsi e dimostrazioni matematiche intorno alle nuove scienze, Iacoviello. We found that the first observation that it is the cross-section, the main geometrical parameter that should be considered for the mechanical resistance of a component, of a specimen, we can say. In this case, we are talking about ropes, for example. We have the first drawing of a tensile test on a large body, and also he understood that the direction of loading was important to determine the mechanical behavior of a material. Well, in the year after, we have many other discoveries. For example, we can recall among them Robert Hooke. He was the first salaried scientist in European history at least. And we can recall the maxim utensio sic vis, and it is the basic of the linear elasticity. Obviously, in Europe, we are so used to be focused on our own history that we often forget that there are many other ancient civilizations, for example, China. And obviously, we can only find two important examples. For example, the Zhangzhou Bridge, that is the world's oldest fully stone open-span segmental arch bridge, and it is one of the ones I think we can show in the picture on the left. And also, being a metallurgist, we can talk about the malleable cast irons. We discovered in Europe these kind of alloys at the end of 18th century, but in China it was already produced in the 4th century before Christ, I mean 2,200 years before the discovery in Europe. And well, the crucial point for the structural integrity is probably the Industrial Revolution. Up to the Industrial Revolution, the main components produced by metals were swords, guns, and well, the damaging mechanism was always connected to overload mainly. With the Industrial Revolution, we have new way of unloading components, for example, cyclic loadings, and we have also some problems in some critical environments. So we have here a list, a short list, but the problems were more evident. A short list of catastrophes in the centuries, in the last 2 centuries, concerning bridges, dams, I don't know, trains, planes, etc. And well, with this revolution, we had new damaging mechanism. A really modern damaging mechanism is probably fatigue, because before the Industrial Revolution, repeated loading were not so frequent on a component. And as you can see in the more or less 150 years, 2 approaches for the analysis of this mechanical behavior. One approach was connected to analyze the damaging mechanism in alloys. I mean, identification of the crack as the reason for these problems, because in the first year of the 19th century, researchers thought that there was a sort of mysterious transformation of the structure of the material from ductile to brittle. Instead, for example, Rankine, Fairbairn, Ewing focused their attention to the nucleation and growth of fatigue cracks. But also we have other approach with the focus on the fatigue life, determining the fatigue life for a load, an applied cyclic load, for example, with Wheeler, on the determination of the infinite life condition. Well, at the end of the 19th century, it was clear that an approach based on the analysis of the static load tensile data, or also the Wheeler fatigue curves, must remind you that the fatigue curves were identified as Wheeler curves only in the 30s year of the 20th century. Anyway, it was evident that in case of sudden blow or severe environments, for example, cold environments, these 2 approaches were not sufficient. And in this case, the optimization of the Chappie test was clearly a new approach to analyze the behavior of components and materials. This approach was really important. For example, it was on the basis of the solution of the Liberty ships problems. You know, there was cracks that could create big problems on these ships that was produced with a large applying of the welding. And it also allowed to determine the ductile to brittle transition temperature. But this test had some inherent limitations. I mean, first of all, everybody knows here in this stage, we can remember the measured absorbed energy is highly dependent on the displacement size. So in the beginning of the 20th century, we had the new science, the fractional mechanics theory, with the first works of Griffith in 1920. Then we have Irwin in 1957 with the concept of K-first and K-first-C characterizing the brittle fracture resistance, the linear elastic fracture mechanics. Obviously, J. Rice and the J-integral concept extending its applicability to the elastic plastic fracture mechanics. And then after these, obviously there are many other names, I'm just cutting for the limit of this presentation. We have 2 important standards, ASTM E399, standard test method for linear elastic plane strain fracture toughness of metallic materials, And the E1820 standard, the standardized method for measurements of fracture toughness. Well, the path to these new standards is quite long. It was not determined in a few days or months. Just the year after the Irwin works in 1958, it was established the STM Technical Committee E24 on fracture testing of metals. In 1966, we had the E39970T. T stands for tentative standard. And after an extensive round-robin test programs, only after that, we had in 1970 the first publication of the E399 standard. And only after 30 years from the Irwin results, we had the publication of 1820, STM E1820 standard. And only 6 years ago, we had the new STM E1820 standard, removing the evaluation of KFRC from this standard in order to avoid the application with the STM E399. Well, after decades of standardization, experimental works, and many results, we have now many relationships between, for example, toughness and yield strength. And for example, in this bubble diagram, we can find, for example, the area describing the behavior of metals and other materials. Obviously, there is always place for also analysis of behavior of new materials, for example, nanocomposites, and it is my pleasure to introduce you, Sabrina.
While we have already seen how fracture toughness is addressed in metals, I will turn now to innovative materials and nanomaterials, where challenges and opportunities are quite different. It's well established that methods for computing fracture toughness, one confined to high specialized fields, are now rapidly expanding into more traditional branches of engineering, as standards originally developed for metallic materials are being extended to applications involving, for example, concrete and rocks. In parallel, advances in material research have not only refined procedures for traditional tests, but also fostered the development of entirely new investigative methods. In this context, my presentation will focus on 2 types of advanced materials: an innovative earth-based material and nanomaterial, presenting a method to compute fracture toughness for each. Let's start the discussion with a proposed procedure for fracture toughness evaluation of quasi-brittle materials. The main feature of this method, called modified two-parameter model, is its ability to account for possible crack deflection or kinked crack even under far-field mode 1 loading, and to assess its effect on fracture toughness. The method builds upon the framework of the original two-parameter model proposed by Shah et al. To determine the mode 1 plane strain fracture toughness of plain concrete and incorporate it into RILEM recommendation. Therefore, I will begin by outlining the main steps of the original method. The specimens have prismatic shape and present a notch in the middle part, in the lower part of the middle cross-section. The specimens are tested under 3-point bending and crack month opening displacement control. More precisely, the specimen is monotonically loaded up to the peak load Pmax, Then the post-peak stage follows, and when the force is equal to about 95% of the peak load, this specimen is fully unloaded and then reloaded up to fail. The elastic modulus, according to Tada et al., is computed by exploiting the specimen geometry and the measured initial compliance CI. Assuming a crack propagation under pure mode 1 loading, the fracture toughness, the effective critical crack length A underline is computed from the measure unloading compliance U, while the fracture toughness is obtained from the maximum load Pmax and the function here reported. But what happens when the crack propagation is under mixed mode loading? A modified procedure is proposed, assuming a kinked crack with one branch characterized by an orientation theta. The elastic modulus is calculated as previously discussed, while for the effective critical crack length calculation is needed to distinguish between the case of a crack with a short branch to that of a crack with a long branch, since the energy release rate changes accordingly. The boundary between these two cases is represented by the ratio A1 over A0 equal to 0.3. Let's start with the crack with the case of the crack characterized by short branch. By applying the Castigliano theorem, a different expression for the elastic modulus is derived, from which the length A1 can be calculated and consequently A underline. The fracture toughness is obtained by assuming a straight crack having a length equal to A underline. When the crack has a long branch, the crack is assumed to consist of two segments, named A1 and A2. In this case, a new expression of the elastic modulus is derived, from which the length A2 can be computed and consequently A underline. The fracture toughness is computed as previously discussed. But now let us move to the application of the proposed procedure to an innovative earth-based material. The material is composed by a mixture of excavated soil, aggregate, cement, steel fibers, and water. The dry mixture is blown by high-velocity air stream into a spray hose. Water under high pressure is added to the above mixture stream by a separated hose in correspondence of the spray nozzle. The impact onto the surface compacts the material. The applications are those typical of dry shotcrete and may consist in new structures, repairs and rehabilitation, and slope and surface protection. More precisely, the material here examined consists of 7 parts of excavated soil, 7 parts of aggregate, 2 parts of cement for stabilization of soil, 1.5% of steel short fibers by volume, and about 3% of water. The formwork panel is left to curing at about 33 degrees of temperature and about 50% of relative humidity for about 2 months. The specimens for fracture toughness evaluation are extracted from such a panel. 6 specimens are tested under 3-point bending by using an instrument testing machine under crack mount opening displacement control by employing a clip gauge at an average speed equal to 0.2 mm/hour. The load acts in the material's bi-direction. In this slide, the load, crack mount, opening displacement experimental curves are reported and used to compute, to measure the initial compliance I, the unloading compliance U, and the peak load Pmax. Also, a typical crack path is reported on the right-hand side. In this table are summarized the results obtained. The average value of the fracture toughness computed by applying the modified two-parameter model is equal to 1.16 megapascal. The corresponding value obtained by applying the original method, that is the two-parameter model, is equal to 1.274 megapascal square meter. Therefore, the method proposed provides a lower value of the fracture toughness, less than about 90%, with respect to that provided by applying the two-parameter model, which can be regarded as a conservative result. Now, let us move to the procedure proposed to evaluate the fracture toughness in nanomaterials. That is, structures with one or more sizes measured in the nanometer scale range and manifesting the so-called size effect. The method here proposed to compute the fracture toughness follows the same framework of the 55281 ASTM standard, proposed for laminates with a polymer matrix, here briefly summarized. The specimen consists in a double cantilever beam containing a pre-crack with a length L. The ends of the specimen are open and the load, the force F and the length L are recorded at the time instant when crack propagation is visually observed on one side of the specimen by means of a microscope. The fracture toughness is computed from the energy release rate by assuming a plane strain condition. Moreover, in nanomaterials, the forces that are completely irrelevant at the macro scale, such as long-range interatomic and intermolecular cohesive ones, significantly influence the mechanical response of nanomaterials, that is, size effect is present. Therefore, a different expression for the energy release rate has to be derived in order to take into account such a size effect. Let's model the testing setup by a double cantilever beam. Firstly, a novel theory named stress-driven non-local model is employed to derive the transfer displacement of a cantilever beam with a length L and loaded by a force F. The material characteristic length LC reported in the displacement relationship is related to the material macrostructural properties, such as lattice sizes, grain sizes, or atomic bond length. Then, by exploiting the energy release rate definition and the Castigliano theorem, the energy release rate expression is derived where lambda is the normalized characteristic length, the normalized material characteristic length, that is equal to LC over L. Finally, the fracture toughness is obtained from the energy release rate by assuming a plane strain condition. In this slide is reported the fracture toughness normalized with respect to the classical solution against the dimensional characteristic length, lambda. It can be observed that the proposed proposed procedure is able to capture the above size effect, and by entering in this graph with the given value of lambda, the value of the fracture toughness can be simply obtained. And now let us move to the application of the proposed procedure for fracture toughness evaluation of a crystalline silicon with a 100 crystallographic orientation. The material was experimentally analyzed by Java et al. By considering different testing configurations and obtaining a value of the fracture toughness equal to 0.8 megapascal square meter. Among the different testing configurations analyzed by the authors, that of a single cracked cantilever microbeam with sizes 5 for 20 microns is here considered for lambda calibration. The crack had a length of 2.3 microns perpendicular to the beam axis and located at a distance of 2.5 microns from the constraint end. 5 specimens were tested. But with a value of lambda equal to 0.03, the analytical curve fall inside the experimental scatter band, and elastic behavior is well captured. It worth noticing that lambda equal to 0.03 correspond to a material characteristic length LC equal to 0.55 microns, which is consistent with the material grain size. By applying the fracture toughness is computed by applying the relationship proposed, obtaining a value of the fracture toughness equal to 0.83 megapascal square meter, by assuming a value for the classical solution equal to 0.95 megapascal square meter. It can be observed that the result obtained is in satisfactory agreement with the experimental data, experiencing an error less than 4%. This concludes my presentation. Thank you for your kind attention.